Hi everyone. It's 5 p.m. my time in London here. Um, we can leave a couple of minutes and then we can start. Yeah, I see people joining. Okay, I see more people joining. Yeah, I think we can start at least with the presentation and the introduction. Hi everyone, thank you for attending to this talk in KDD. I hope you are guys enjoying this unusual conference. Today we're going to present IDs, Jianxun, Le, and my name is Miguel. We are in complete different places. I'm in London, Le is in Singapore, Jianxun is in Beijing, and IDs is in Redmond. So very interesting, different people from different places. And we are going to talk about something that we did recently, which is how you can do recommendations of papers related to COVID-19 using a knowledge graph. And we are going to guide you and do a hands-on tutorial on this. All the code is available for you to reproduce. And so this is as you can imagine, the idea of this work is the COVID that took us all, surprised us all, and well, you see the 23 million cases and 8,000 deaths, which is really crazy. I always say that for us engineers and computer scientists and data scientists, it's not easy to help in a similar way that doctors help. Like, I have friends that are doctors, and obviously they are really the heroes here. So I mean, we can maybe facilitate the work of these people, right? And that's kind of what we wanted to do. We want to facilitate the work of people that are looking for answers and how to better solve or find a vaccine to the COVID-19. So that's what this is about. So this tutorial, we want to do a recommendation search for COVID-19 papers, and we include a knowledge graph. And there is a data set called CORD-19, which is a data set of all related papers for COVID-19. And we're going to talk about different graph-based techniques and implementations. We have a repository called Microsoft Recommenders with many different recommendation algorithms available in open source. And also we're going to talk about the knowledge graph, Microsoft Knowledge Graph, called a Microsoft Academic Graph. And finally, we're going to talk on how these algorithms can be operationalized. And I think one of the most important thing is that you have access to the material. Hopefully, if any of you want to run the code while we are giving the speech, you can do it. Hopefully, you guys have installed the dependencies. If not, you can go. Sorry, you can go here. So this is the page where so the presentation page where we have all the information, and I think here. Oh, sorry, this is not working very well. So let me do it like this. Yeah, this is the where the code is. Here you have all the scripts. And here you have the YAML file to be able to install the Conda environment, right? So you just execute this this file, and everything should be installed, and then you can start running the different notebooks. Okay. This is the structure of the talk. We're going to well, first the environment setup. Which basically is what I said. We're going to talk about the basics of the dataset CORD-19 and the knowledge graph. We're going to understand what are knowledge graphs, what kind of applications can knowledge graph empower, and then we're going to talk about some algorithms that can be used on recommendation systems with knowledge graph. And the last part is how to operationalize and how to deploy these kind of algorithms. And at the end there is just a Q&A. So yeah, this is the environment setup. Just what I said. Go to this page, and you just need to clone the repo. The only thing, so the repo is Microsoft Recommenders. The only thing you need to make sure is that you are on the branch KDD 2020 tutorial. Okay. And this is the path where the code is. And you just need to run the code environment. I think yeah, this is the step. I don't know if we want to wait a little bit, or should we go directly to the first presentation? I don't know if people can. Yes, here we have all the participants.
I think probably we can have some time for people just to figure out for example, if they can access the link we share, and if they can find the right place to, for example, set up the environment. And maybe because the setting up everything take 5 minutes plus 10 minutes, and maybe we don't really want to stop here, and we can proceed with the lecture for the next module. But people, at least for this part, we just want to make sure that they have access to all of the resources. Yeah. And yeah, definitely, maybe if the audience, you have any questions, just feel free to type into the chat box. Yeah.
Yeah, definitely. Any question, we'll try to answer.
Yeah, maybe we can like have another 4 minutes, 4 to 5 minutes. Yeah.
Yeah, makes sense. going to stop my video. Unable to access. There is a person. So. This is what you should do. Yeah. Check out. That's really weird. Manasa is having an error. Okay, so there is a person answering Manasa. Okay, so guys, it's 5:15 in my time. I think we can get started with the first presentation. At the same time. Yeah, I think we can get started, and then yeah, in the meantime, we will keep take a look at the chat to see that nobody is blocked. Okay, I'm going to stop sharing my screen, and I'm going to give the word to Alexander. Alexander, are you there?
Yep, hello?
Yeah.
Okay. So first video?
Hello, everyone. This is Iris from Microsoft Research. Welcome to our tutorial. In this module, I will introduce the basics of the CORD-19 as a text corpus dataset and a scientific knowledge graph, and how and why we are interested in linking these two datasets together to empower more application scenarios. This is the overview of this module. We will introduce two datasets. One is the CORD-19, which includes metadata and the full text documents. Another is a scientific knowledge graph, Microsoft Academic Graph, or MAG. Then we will talk about how to establish the linkage between these two datasets. We will answer the who, why, what, when, where, and how questions on both datasets, as well as the linking operations. So, why do we think this content is valuable to share, and this could be relevant to your own project or business scenarios? Because we believe that we can consider the CORD-19 as a specific instance of a collection of full text documents with associated metadata, and the Microsoft Academic Graph as a specific example of knowledge graphs. When the metadata of the text corpus can be closely aligned with schema behind the knowledge graph, we can use an index build from the knowledge graph to match the text documents to nodes in the knowledge graph. In most cases, the text corpus size, in terms of the number of documents, as well as topics or contents covered, are relatively small compared with a full knowledge graph. Hence, once the linkage is established, it's not only linking the unstructured documents written in natural language to a structured knowledge graph, but also connecting a smaller and more specialized contents with a larger and richer information in the more comprehensive knowledge graph, where the knowledge graph could have been constructed with much more documents and data sources. Such established connection would bring in richer information into the original text corpus and can help facilitate many downstream tasks, such as search, question answering, analytics of the contents, as well as recommendations. For today's hands-on tutorial, we will focus on showcase the content analysis, and more importantly, the recommendation scenario. So today's focus is we would like to use a connection between the CORD-19 dataset and a scientific knowledge graph behind as a motivating example to enable you, our audience, to think about similar scenarios in your projects and the lines of business, And we hope with a hands-on experience to the end-to-end process, it would give you some inspiration on using the technologies we shared to help you solve your own unique challenges. Let's first introduce the CORD-19 dataset. It's an abbreviation for COVID-19 Open Research Dataset. So why we create this dataset? The CORD-19 has been spreading for months now, is testing all of us in our works and the daily lives. While the challenges and the losses we now face were almost unimaginable just a few months ago, the global research communities across domains are pressingly called for to help establish containment of the pandemic from academia's perspective. The CORD-19 dataset is created to enable AI researchers to produce text and data mining algorithms and tools to help accelerate COVID-19 related research. So who are behind the dataset curation? This is a collaboration effort from multiple leading research groups, including Allen Institute of Artificial Intelligence, AI2, Microsoft Research, Chan-Zuckerberg Initiative, National Library of Medicine at NIH, and Georgetown University. So what are included in this dataset? When it first launched in March 2020, it initially consists of 28,000 academic papers and preprints on COVID-19 and related historical coronaviruses such as SARS and MERS. The collection has grown fast to more than 200,000 papers as of the end of July. We can see we have several main data sources contribute contents on daily basis now, including PubMed, WHO, bioRxiv, and the medRxiv. The input contents include both paper meta information, such as titles, authors, year, publishing venues, as well as full text in the form of PDF or XML. The Semantic Scholar team, or AI tool, lead the efforts to ingest and dedupe the paper metadata information and use their established pipeline to extract the full text information from PDF and XML. Then harmonize the contents and publish a corpus of parsed full text with associated metadata information on daily basis. More details about this dataset can be obtained in this paper shown here at the bottom. And we also provide a few links which you can get the dataset from several mirror sites, including Azure Open Dataset Service, which not only provides the raw contents, but also a Jupyter notebook, which would help you navigate the dataset. Next, let's take a look on the Microsoft Academic Graph. The Microsoft Academic is a project started in Microsoft Research Redmond since 2014. It aims to use AI to help curate all the scientific publications that represent the frontier of the most original collection of human cognition of the world. Why do we need this? According to a recent survey done by the colleague in Semantic Scholar team, the average researchers are reading about 270 papers a year, roughly 1 paper each workday. On the other hand, based on the latest stats from the MAG graph, there are more than 1 million papers published in the month, which is equivalent to a new paper published every 2.6 seconds. This is simply beyond the human cognitive capability to possibly read all relevant research papers. For example, a regular literate person would read at about 200 words a minute, while the top 1% speed readers can cruise at 600 to 700 words per minute. Based on our latest estimation on the paper publishing rate in different domains and their typical lengths, it would take a computer science researcher 27 consecutive days, which means 24/7, to finish reading all computer science publications, titles and abstracts only, published in a month. For researchers in the medical domain, it would take them 54 days, double the time. So how can we resolve the imbalance between the supply or the production side of the mass production of the academic contents and the consumption side limited by our human cognitive capabilities? The short answer is to leverage the machine's cognitive power in memory, computation, attention, and endurance, which are superior to human beings, to help us. So we are deploying intelligent agents to read, remember, and comprehend these scientific documents, and then to organize the knowledge acquired in the graph form, which is our Microsoft Academic Graph. This scientific knowledge graph contains information around when a paper is published, at which journal or conference, by whom, and the citation relationships, as well as to construct the semantic understanding of the contents by recognizing what topics each paper is talking about. Even the term may not explicitly showing in the text. These would not only facilitate and help individual researchers and professionals to more efficiently find and curate the relevant and the most up-to-date works published to their domain, hence to increase their productivity and help them more focused on most important tasks in research, their original discovery to further push the frontier of science. And such scientific knowledge graph can also provide a holistic view on the overall research landscape and the most recent development trends for research institutions and the policymakers, to facilitate them to make important decisions such as how much to further invest in specific research domains, or how to leverage the latest AI development to achieve their own missions. I also include a few links on the project details and how to request access to the full graph for free, and 2 papers on the project design and the more comprehensive review are also included at the bottom. After we have the high-level understanding of each individual dataset, let's talk about the linkage of these two. Why we are interested in linking them? Because even the CORD-19 itself have the metadata associated. However, the metadata are still string or text-based, which means that there is no semantic meaning behind it, and such metadata content could also be noisy as their minimum data cleaning or normalization has been done on the CORD-19 dataset generation. At the same time, the information like paper title, author, journal, or DOI in the CORD-19 metadata are highly aligned with MAG schema design. So if we would link these two datasets together, it will bring a richer semantic information from the knowledge graph to the text corpus. That would empower better results on several downstream applications, like search and recommendation. Lots of them are mentioned in the cited CORD-19 papers. In this tutorial, we will focus on two applications after the linking. They are the content understanding and the recommendation. We know it's important and beneficial, and how can we achieve this? Paper in CORD-19 to paper in MAG linking. We will leverage the inference engine developed by the Microsoft academic project, which is called MAKES, representing Microsoft Academic Knowledge Exploration Service. Essentially, it is an index build based on the MAG knowledge graph content, and it would take a text string which very similar to a reference entry appears at the end of each academic paper, which may include partial information about the paper meta info, like title, first author name, abbreviated publishing venue, DOI and the years, etc. Given such an input, the inference engine or MAKES can return the most similar paper entity. MAKES API is also used to power the Microsoft Academic Search frontend. That is, to use the index knowledge graph to support semantic academic search. More details about MAKES can also be found in this reference paper. In this slide, we will explain on the process about how we get the dataset mapping. First, we need access to three things. The first is to download the CORD-19 dataset. The second is to request the access to Microsoft Academic Graph. And the third is to get access to MAKES API or the Search API. Once we have the access to all of them, in the first step, we will use the concatenated metadata of each paper in CORD-19 to call MAKES API. It would return the corresponding mapped paper ID in MAG. Once we have the set of paper IDs in MAG, we can use that to run a PySpark script to retrieve a subgraph of MAG, which contains only CORD-19 paper titles, paper entities, as well as associated author, journal, affiliation, and the concept or field of study entities. This subgraph is only about 0.1% size in terms of the nodes compared with full MAG graph. When this subgraph is ready, we can continue on the application scenarios in following modules. We designed this tutorial as a hands-on session. However, several steps in Module 1 are required, sending requests to get the MAG or MAKES access on Azure, and API runtime to get the full paper ID mapping, which may also take hours to get the 200,000 API calls all finished. We have included detailed step-by-step instruction on the web pages with sample codes shared there. We will not reserve specific time for you to finish during this session. You have the option to either do it step by step on your own either before or after the assigned tutorial sessions, or you can directly get the mapping results from the web links, which the data size is quite small, in total less than half gigabytes, so that you can continue following lab sessions on your own VM without any issues for the following modules. At last, let's have a quick summarization on what has been covered in Module 1. We mainly introduced two datasets, CORD-19 and the Microsoft Academic Graph, mostly emphasized on what are included in these datasets and why we build them. Then we talk about how we can link these two datasets and why we are interested in the linkage. We hope this can help our audience to generalize to a broader problem setting, which essentially having a smaller and specific text corpus with some sort of metadata associated, and a larger and more comprehensive knowledge graph behind. If it would be possible to build an inference engine to index the knowledge graph and link these two datasets. Once the link is established, then we can leverage the global information from the knowledge graph to facilitate downstream applications on the given smaller specific text corpus, such as better semantic search, Q&A, content analysis, and last but not the least, recommendations to help further proactively exploring on the most relevant contents. So these conclude Module 1. I hope you enjoy our tutorial so far, and see you in the next module.
So Alessandra, maybe you want to stop here for a while to let the audience to ask some questions regarding the Module 1, if there are any.
Got it.
By the way, if any of the audience, if you want to ask a question, I can probably help you unmute, and so that you don't have to type. But before that, maybe you want to type in the chat box that you want to ask something. Yeah. All right, if there's no question, probably, Alexandra, we can proceed with the next module.
Sure.
All right, thank you much.
Hey, hello everyone. Welcome back to Module 2. This is Iris. Earlier in the first module, we have talked about the CORD-19 dataset and the MAG, as well as how to link them to generate a CORD-19 MAG subgraph. In this module, we will use the subgraph generated to help us understand what's in the CORD-19 datasets and some interesting insights that we could discover. In Module 2, the theme is to understand the contents in the CORD-19 corpus. We are going to compare the size of the subgraph with the full graph, and also dig deeper on certain part of the knowledge graph schema. We are also going to explore the CORD-19 subgraph by slicing and dicing along different dimensions, such as by temporal dimensions, by geographical regions, and by publishing venues, etc. One of the most important dimensions is the topic in the paper. We will dive deeper on how the topics are recognized and stamped for each article in MAG, as well as to provide an alternative option to recognize academic concepts in any given text, even if it's not a publication node to MAG. These can be achieved by using a tool we released together with MAG called Language Similarity API. Now, let's first compare the size of the full graph with the CORD-19 subgraph. On the left is the CORD-19 subgraph, and on the right is the full MAG. We have put the side-by-side comparison on the size and the relationships. We can see that in CORD-19 subgraph, we do not have any publications in conferences, so the conference node type is gone, and there are no patent nor book are included in the CORD-19 subgraph so far, based on our June snapshot. We can also tell that the number of nodes, including all types of nodes, mainly dominated by paper nodes and author nodes, in CORD-19 is about 0.1% of the full MAG, while the topics covered by this corpus is less than 8% of all topics available in MAG. CORD-19 is indeed a much smaller and specialized corpus compared with MAG. Hence, when we use a matched paper ID on CORD-19 data to generate this subgraph, it reads the full MAG at 500 gigabytes. It requires distributed environment to efficiently extract the subgraph. We use a PySpark on Databricks to achieve this. Once the smaller dataset is extracted, it only has half gigabyte size. We can efficiently run Panda script to further explore and analyze the CORD-19 subgraph on a single VM. This is what we will do in the lab session in this module 2. In this slide, we will provide the pointers and the information on the MAG data schema. On the top, we have the link for detailed MAG schema information. If you need to understand some specific column meaning or data type to write your own query, Please refer to this page. For the CORD-19 subgraph, as we just said, it only has a small portion, say 0.1% of full graph. We still keep the subgraph schema identical to the full one. Hence, the scripts that we shared to manipulate the CORD-19 subgraph, in theory, shall also be applicable to full MAG. However, due to the size constraint on full MAG, which is 500 GB, it is infeasible to operate that size of data on a single VM with Pandas. We provide the sample codes with identical or similar functionalities on PySpark so that you can run it on distributed environment on full MAG to do similar analysis. Among all the tables and the relationships in MAG, we would like to emphasize on the topic-related nodes and edges. Why are we so interested in them? Because the concept or field of study is the only abstract entity type in MAG, which represents the semantic contents of a document. Unlike physical entities, such as authors and affiliations, concepts are abstract and therefore there is no concrete way to define them. In MAG system, we have identified in total more than 740,000 concepts from both external data sources, such as Wikipedia or UMLS, which is the Unified Medical Language System. And we also directly mine emerging concepts with a self-supervised concept extractor that extract terms from MAG titles and abstracts. We use a subsumption-based model to construct a 6-level taxonomy with top-level domains and the subdomains manually curated for the sake of accuracy and stability. All remaining lower 4 levels are completely automatically constructed by algorithms with minimum human intervention. Here in the table, we give some examples of the concepts in MAG, as well as their position in the taxonomy. We also maintain relationships between concept pairs other than just parent and child. For example, if 2 concepts are frequently co-mentioned in many documents, they are considered as related. We also have relationships like a disease with associated symptom, or a treatment can be used to cure a certain disease, etc. All these relationships are maintained in these 4 tables shown on the right, among concepts themselves, as well as between concepts and papers. These are the relationships that constitute a sub-knowledge graph, which would be used for our next module about knowledge graph assisted recommendation system. For more details of how we recognize the concepts and build the taxonomy, please refer to this 2018 ACL demo paper and the blog post shown at the bottom of this page. When we are going to recognize concepts in an academic document, there could be 2 possibilities. Either the document is a published paper that is already indexed in MAG, or the document is proprietary one and cannot be recognized as a public node in MAG. We will discuss how we do the field of study stamping on documents in both scenarios. In this slide, let's first look at the case that the paper node is in MAG, how our system stamps a paper with appropriate concepts as well as domains and subdomains. When the paper is a node in MAG, it has both language features, such as the natural language text in titles and abstract, and structural features, such as its neighboring nodes, either in the same type neighboring nodes, which represent the citation relationships, or some different types of neighboring nodes, which represent the relationships like authors or publishing venues. Same to a paper node. For each concept node in MAG, it also has both language features, its description, as well as structural features of its neighboring nodes. For both language feature and the structural features, we can represent them in discrete space, such as n-hop vectors and the continuous space, using word embeddings or heterogeneous graph embeddings. Then we can construct a mixture model to represent the concepts and the publications, and use cosine similarity to measure the distance between each other, and apply a heuristic nearest neighbor search to tag concepts to documents. The word embeddings are trained on academic corpus in MAG, which would yield better results on tagging compared with other pre-trained vectors on general domain corpus such as Wikipedia. Again, please refer to this ACL demo paper for more details if you're interested. In this slide, we show the results generated by this Module 2 hands-on tutorial script on CORD-19 subgraph in terms of topics in top-level domains and the subdomains. We provide the detailed instruction on how to run the hands-on tutorial script, and we will go over the scripts together to repro all the analytics results shown in these and the following slides later. With this specific version of mapped subgraph, we can see that on the top level, with no surprise, more than half of the CORD-19 papers are in medicine domain, and another 30% are in the biology domain. The biomed in total consists of 85% of the corpus, and top 5 domains represent 93% of all papers. When we further explore the subdomains, they are more diversified. Since top 10 subdomains altogether only represent 57% of all papers, and the virology and the immunology dominates the subfields discussed in CORD-19 subgraphs. All these results shown in this slide are based on the fact that CORD-19 papers are reliably linked to a paper node in MAG, and the concept tagging are done as part of MAG corpus generation pipeline on weekly basis. So what if some CORD-19 papers or any other proprietary documents which cannot be mapped to any node in MAG, but we would still like to use some tools to understand what the documents talk about. For example, some clinical trial documents or some patent filing documents haven't been submitted, or funding proposals received by government agencies. We will discuss how we can achieve it in the next slide. One of the solutions to such proprietary academic documents concept tagging is to use a tool called Language Similarity API Package released with MAG distribution. It wraps the language feature part of the module we just described earlier into a package implemented in C#. It provides 3 methods to compute similarity between any 2 pieces of text or between a text and a given field of study in MAG, or it can recognize a list of relevant concepts with associated confidence score when given a natural language text as input. The model saves all the semantic information about words, which is learned by reading over 100 million English paper titles and abstracts. Then it can infer what topics the input text is talking about by reading it. The detailed usage and examples are described in the MAG documentation site, as well as this blog post shown at the bottom of this page. Currently, we only publish a C# version of the Set Language Similarity API, and we are working on a Python version and hope to publish it soon. Please keep tuned on the updates. In next a few slides, we will go over more analytics results around the CORD-19 subgraph on publishing venues, geographical regions, as well as team size. In this slide, it answers the question, where did the CORD-19 research paper publish? Here is the top 10 publishing venues in terms of the number of papers published. We can see that the Med archive and the bioarchive are playing a very important roles as it supports the open access of published papers, as well as preprint services before they are scheduled to be in print for the accepted journals. From the top journal names, it also helps us to cross-validate that lots of CORD-19 papers are in subdomains of virology and infectious disease, as the journal name suggests, and it is also consistent with the top subdomains that we just saw a few slides earlier as virology and immunology. In this slide, we can look at how the CORD-19 research has been produced by different geographical region researchers over the years. Even year 2020 is just halfway through. Collectively, there are between 1/3 to half of the paper in CORD-19 are published in this year, 2020. And we can see United States, EU, and China dominate the COVID-19 research and the publication. Another interesting topic, in general, when people analyze the bibliographic data, is to compare the productivity and the impact of research produced by smaller groups versus medium and larger groups. The CORD-19 subgraph suggests that, collectively, smaller groups are more productive in terms of the paper produced over time. However, it's definitely worth of diving in with the trends over years to see the evolution of collaboration patterns between researchers. Let's summarize Module 2 with this slide. In this module, we have focused on the CORD-19 content understanding with the assistance from the knowledge graph. We have touched the size comparison on the CORD-19 subgraph with the full MAG graph. Then, we introduced the MAG schema with an emphasis on the concept-related parts, as well as discussed how we design and implement the most challenging part of the MAG construction, which is to tag each paper with appropriate concepts. At the same time, we also explained another tool that is provided in MAG distribution, Language Similarity API, that can be used to tag independent academic documents without forcing it to be a paper node in MAG. At last, we go over several slides of CORD-19 content analysis results to understand its distribution across different dimensions. In a nutshell, in Module 2, we have shown once we have a text corpus with metadata, link it to a more comprehensive knowledge graph behind, we can leverage the rich semantic information from the knowledge graph to help us better understand the content and the distribution of the given text corpus. Next, I will hand over to my colleague Chieh-han to go through the hands-on part of Module 2 to run the Panda scripts and repro all the analytics results we shared earlier. Then we are going to transition to Module 3, which is talking about one of the most important applications, Knowledge Graph Assisted Recommender System. Thank you again for attending our hands-on tutorial session. I hope you find the materials relevant to your project, and feel free to reach out to me if you have any questions related to this tutorial or knowledge graph in general. Thank you, and bye for now.
Hey, hello everyone. This is Iris speaking. So yeah, my colleague Jianxun has some other family engagement. So I'll continue to quickly go over the Panda or the Python script using Panda to generate the above mentioned analytics on the CORD-19 merge with Microsoft Academic Graph. Let me share my screen. Hey, hello, can you see my screen properly?
Yes.
Okay, yeah. So you see, it's actually quite straightforward if you are familiar with Panda, or even you are familiar with the SQL style script. It's actually mostly follow the SQL style data query and the generation, and using the Seaborn and to do some graphics plot. So you can see that first, at the very beginning, we import this Panda Mag class. which we already generate a class script so that it will facilitate you. If you have a smaller subgraph, you don't have to manually to input all this column information. You can only have one line of code so that you can directly get all the table information. So it's actually pretty straightforward. As long as we get the data frames with specific entity types, we can get all this information. So you can see we have the papers, and then we have the paper author affiliation information. And here is we get a field of study as well as what's STEM, the field of study associated with a paper. And here, these are the journal information, as well as the raw entity affiliation entity information. So from here below onwards, we will have to generate the top K journal. Here, I believe we generate the top 10 journal which the CORD-19 papers are published. So you can see here is the printout table result, and by using this bar chart plot, we can generate this. This is identical as the result we showed earlier in the slide. So this is the venue part, and the next part, we actually generate the team size. So the team size is obtained from the paper author affiliation. So in general, each paper have how many authors, or we call how many co-authors. So you can see if we run the recalculate. So you see on average, we can tell that a paper published in the CORD-19 have about 6 authors or a team size of 6. And if we further bring down the team size to different bucket, and you can like update the bins as you wish, and then we can see that we have the team size distribution result. Here another bar chart. Again, sounds like in the medical domain, still the majority of the content are conducted by relatively smaller size of the group. So this one is try to understand where does those publication coming from in terms of the geolocation. So this one is a separate input data we uploaded to the Git, because it's not part of the standard Microsoft Academic Graph yet. But we are going to add this part, and we'll update the corresponding script accordingly later, very soon. I think the benefit for having this geo information is would be very interesting to analyze where does the research group or the researchers are coming from in terms of the geo or the country location. So you see that here we get the affiliation, and we get the affiliation region, and also we try to slice it by the time, by the year. So you can see that overall for the past 20 years on the CORD-19 data, we can see here is the overall trend. Still the United States still dominant the research, and then followed by the EU and China. So the very last part are on the field of study distribution. The field of study, as we mentioned earlier, in total we have 6 levels. So here the distribution are focused on the top domain level, which are mostly dominated by the medicine, biology, and the chemistry. So yeah, these are the contents, how we can generate the top domains on level as 0, and also what's a percentage of each domain. You can see that more than half almost 55% are coming from the medicine, and about 30% the biology, and all the remaining are relatively small, which without surprise. So the next one is the next one is for the L1 level. We call it as a subdomain. So the subdomain actually is a very how to say diversified. So we can only get these virology as a 26% because these are the 26% of the total top 10. If it's considered as all paper, I believe the result is relatively very small, only 5% or 4%, because in total we have almost 200 different subdomains. So it's a very it's no longer that easy for a top subdomain dominant as 20% in the total corpus. So here we have this distribution, a pie chart, and so the next part is just the paper per domain or subdomain, the increasing trend over the years. So you can see that like earlier on, it seems like in the CORD-19 data set, we can still, the biology or the medicine are on par with each other. But for the recent years, the medicine domain are significantly dominant than other fields. And the below are the same, which are nothing new, just in terms of the subdomains, you can see the trend. So also, so these are the scripts, and I would like to also show that there's another way to get this the CORD-19 data directly through this API. If you, I have the link in the earlier slide. If you have subscribed to this project academic knowledge API, and then once you subscribe, you will get a key, subscription key. I believe, oh yeah, so with the key, actually we can get the paper for the paper. We can get the paper within the academic with the academic graph with the CORD-19 junction, the subgraph. So here we have the sample API call. So what I'm doing here is just copy this sample to here, right? So replaced with my own subscription key. So it returns the top 10 machine learning papers exist in the CORD-19 dataset. So if I parse the result here, you can see that it's a JSON result. So very top one is the deep CNN aided detection, and I don't know why it's in the CORD-19, but obviously it's being included. Yeah, so you can see that you can modify based on here. We can change the name. If it's instead of machine learning, I don't know. Let me see. I can change the term from the machine learning. Say I try deep learning. Okay, it gives us a new set of the content, which is yeah. So you see, it's been updated. You see, these are the different set of paper. Are the top rated deep learning paper appeared in the CORD-19 dataset. Yeah, that's what I have. And also here is a link if you like to try using the language similarity package to stamp your own texts, which are not publicly available or not publicly shared you can always try this. And as long as you subscribe to the Mac graph, it will be a part of the package. And you can see how it works for your corpus. Yeah, I think, and maybe I can have a quick point out because someone asked the question earlier. So here we have like the daily or close to the daily release of the Microsoft academic graph to the CORD-19, the ID mapping release. So for this pre-recorded tutorial, I believe we are using an earlier time, like either the June 16 or 14 date for this. But if you do want to follow the instructions step by step from the beginning, I would strongly encourage you request to get the latest version of the MAG, which is like 4 days ago. We kicked off last Friday when we released today. Actually, we released yesterday, and also the latest CORD-19. And you can get this mapping and then start using the PySpark script to generate the subgraph and do the following steps. Yep, that's all I have. So do any of you have questions related to either this part or the first part? Yeah, if you don't, I guess I will stay until the end of this tutorial. So if you have anything more want to check, I'll also be happy to answer at the very end. Otherwise, I'll just stop sharing and yeah, Alexandra, you can help us to continue the module 3. Thank you.
Welcome to this section. My name is Jianxun Lian. In this section, I will introduce some applications of knowledge graphs in the scenarios of academic recommender systems. The goal of this section is to provide you with a hands-on journey of building a real recommendation system. Here is the outline. First, I will introduce the background, including our task definitions and the code base we are going to use. Then I will introduce the model, DKN, which is a knowledge-aware deep recommendation model. After that, we will switch to Jupyter Notebooks. You can follow us step by step from data preparations to DKN model buildings to final evaluations with baseline. So first, let me introduce what task we are going to do. There are 2 tasks, including You May Cite and More Like This. You May Cite is a user item recommendation task. Given an author, we will learn a model to recommend a list of papers for him to read and cite, based on his previous citation history. The second task is More Like This. Given a research paper, our task is to recommend a list of related papers based on the content, so that readers can continue reading. You May Cite and More Like This are 2 most typical applications in recommendation scenarios. Knowledge entities used in this hands-on tutorial is field of study of the research paper. Field of study is an area of academic concentration. Here I give an example of 2 papers titles with their knowledge entities highlighted in red. In the first paper, there are 3 knowledge entities in the title. In the second papers, there are 2 entities in the title. Knowledge entities are not isolated. They are connected by various types of relations. For example, one field of studies may belong to a child of the other one's field of study. And one field of study may be disease. Another field of study may be treatment. They may be connected by a relationship such as treatment to disease. Knowledge entities, together with their edges, can be organized as a graph. We use Microsoft Recommender as a code base to run our hands-on tutorial. You can visit Microsoft Recommender through this link. Microsoft Recommender is a galaxy of examples and practice for building recommender systems. It includes various types of components for building recommendation systems, including data preparations, model buildings, and selections, evaluations, and infrastructure construction. The goal is to help researchers and developers to quickly select prototypes, demonstrate, and productionize a recommender systems. We also hope to accelerate enterprise-grade developments and development of a recommender system into production. The model we are going to use in this tutorial is DKN, which is a deep knowledge-aware network for news recommendations. It is originally designed for news recommendations. News recommendations means based on a user's news clicks history, we recommend small news articles he may click on. Since news articles usually contains a few entities, such as celebrity, companies, and location. Knowledge graph is a count of external data resource, which contains a lot of facts. With the help of a knowledge graph, we can better understand the content of news articles, thus give more reliable recommendations. DKN uses knowledge graph embedding techniques to generate latent vectors for knowledge entities, such as trans-E. We use both the entity's own embeddings and his context embedding to represent an entity. Context embedding means the average embedding of an entity's neighborhood. The key component of DKN is a knowledge-aware CNN module, which we call KCNN for short. It is a convolutional network. It takes multi-channel data as input. The channels include word embeddings, entity embeddings, and context embedding. Entities and words are aligned to each other. The structure is very simple and intuitive. On top of the feature map of CNNs, we apply a mask pooling layer to get a fixed length of vector for document representation. After we get the representations of documents, we use an attention network to merge users' browsing history into one vector as user's representation. Then we concatenate the user's vector and the candidate items vector, and go through a two-layer fully connected neural network to get the final prediction score. Okay, suppose now you already have the basic understanding of our task and DKN model. Now let's switch to the Jupyter notebooks for the rest of hands-on section. Open the links, you will see this web page. Let's follow the instructions step by step. First, let's clone the Microsoft Recommender repo. Okay. Our code for this tutorial is placed under KDD 2020 tutorial branch. So let's check out this branch. And the code is placed under the folders of Scenarios, Academies, KDD 2020 tutorial. So let's direct to this folder. Okay. Next, let's download the dataset to this folder. The data downloading process will take a few seconds. After that, there are a few more dependencies you need to install, like the G++ and a conda environments with TensorFlow GPUs, and you need to register the conda environments to your Jupyter notebook. These steps will take another a few minutes. So to save time, I will suppose you already install these environments during our environment setup sections at the beginning of this tutorial. So for now, I will just use my well settings machines for the rest of the step. So let's wait for the data downloading process to finish. Okay, now next let's uncompress the data file. We will uncompress the file into a folder named data folder. Now let's see what includes in this folder. So let's direct it to this folder. You will see that there are two folders. One is my cache, and the other is raw. In the raw folders, it includes all the original text data files of the Microsoft Academy graphs on the COVID-19. For this folder, its purpose is to it includes a few well-processed files in case of some participants who may miss some steps during the hands-on tutorials. If you miss some of the steps, you can simply copy the corresponding data files from this folder to your experiment folders, so you can continue the following steps. Okay, now let's launch the Jupyter Notebook service. Since in my settings I use a remote Linux machine, so I will use this instruction. If you are using your own laptops or desktop, you can just use this instruction. The difference is only that I need to designates an IP address for my remote Linux server. So first, let's direct it back to his parent folders and launch the Jupyter Notebook service and get copies the link. Open it in a browser. Okay, so you will see that the scripts in these tutorials are organized in 5 steps. The first is data preparations, and second is pre-trainings, embeddings, and the rest 3 scripts are for the model training. The first step is about data preparation. We will convert the original data files of Microsoft Academic Graphs into the required data formats for running DKN. First, let's impose the dependency. The first part is about preparing paper-related files. For DKNs, the paper data format is like this. Each line represents an instance of paper with 3 columns. The first is paper ID. The second column is a sequence of words. And the third column is a sequence of entities. Entities are aligned to the words. For example, here is a paper's title: One Health Approach in the Southeast Asia Region, Opportunities and Challenges. There are 2 entities in the title: One Health and Southeast Asia. So suppose this is a sequence of words. You will see that in the entity sequence, the first 2 are the same, because the first 2 words are One Health belong to a same entity, and so are these 3 entity index. For the rest of words which are not belonging to knowledge entities, their corresponding knowledge entity IDs are 0, which means empty. Next, let's assign some data paths. This parameter max word size per paper means that for each paper we take at most 15 words. If a paper contains more than 15 words, we will simply truncate the document to 15 words. On the other hand, if the number of words in document is less than 15, we will simply pack 0 to the right. So next, let's convert the original words and entities into a hash ID. The index will start from 1 because we hold out 0 as empty position. Next, let's convert the original knowledge graphs into the index of triples. So indicating the knowledge graph is consumed as a set of triples in the formats heads, tails, and relation. So let's construct this knowledge graph file with this function. So it will take the original file, which is related fields of study from the Microsoft Academic Graph. Okay, it's done. It's very quick. Next, let's get the whole collection of sentences. We need the corpus of sentence for training word embeddings, which we will do in the second Jupyter Notebook. Okay, it's done. In the second module is about preparing user-related file. In our first task, which is user-to-item recommendation, our goal is to recommend each user with a list of related papers he may be interested to size in the future. So we need to construct a training data set. So the ground truth is from users' citation history. So from first we load the users the author's paper list, which means that we collect all the papers the user has published, and from the papers reference we can get all the papers which this user has cited, and then we sort all the users cited papers by time, and we reserve the last users last one cited paper as the test set, and the last second cited paper for the validation sets, and the rest of the the author's cited papers in for the training data set. So now we have the positive labels. So positive labels means those papers which the author has already cited. Then DKN takes the recommendations as a binary classification problem. So we need some negatives instance also. And for the negative instance, we sample it according to the item's popularity. So yes, so this function will split to the user citation histories into trainings, values, and test sets according to time. Usually, for training our model, we will use a small data set for research the best hyperparameters. So in this function, there is a parameter named item ratio. So for these settings, I set 0.1, which means we create a small data set for parameter tuning, so which is only contains 10% of the entire data set. So we call this data set the small data set, and we use it for quickly select the best hyperparameters, and it will take a relative shorter time. The last part is about preparing item-to-item recommendation dataset. Let's run this cell in the first because it takes a longer time. Different from the user-to-item recommendation task, where the positive labels are easy and intuitive to construct it. In this item-to-item recommendation task, we set up 3 rules to construct the positives instance. A positives pairs means that these two papers are related to each other. The first rule is about paper A's and paper B's overlap a lot in their reference list. And the second rule is paper A's and paper B's are co-cited by many other papers. The third rule is paper A's and paper B's are published in 12 months by the same author, and the first author. We suppose that the author's research interests will not change too much within a short time. So we will generate the positive sets according these 3 rules. A pair of papers are positive pairs as long as they satisfy any one of these 3 rules. Let's wait for it is finished. Okay, it is finished. Next, let's separate the instance into trainings and validation sets and do the negative samplings as well. For For user to item recommendation task, we leave the data generation of the full data sets to the end of this notebook because it takes much longer time. And process numbers equals 8 means we use we use 8 processes to run this data generation function in parallel. So it takes much longer time. It's let it run freely in the background. The second step is pre-training embeddings. DKN takes word embeddings and entity embeddings as inputs. Although DKNs can train the embeddings in an end-to-end manner, it's better to provide pre-trained word embeddings and entity embeddings as a good initialization. So first, let's pre-train the word embedding, and we import the dependencies and set us some iterators and directories, and we use the implementation of word vectors in Jianxun to generate word embeddings. And since it takes a long time to save time, we use a smaller iterator. Let's say it's 4. You can use more epochs for better accuracy. So let's launch this cell. Water vector is simple but very effective ways to generate high quality distributed vector representations for words. And these representations can carry the semantic information of the word. Basically, there are two types of architectures for training word embeddings. The one is skip grants and the other is CBOW. This figure illustrates the structures of skip grant, and in the training process, it uses the current word to predict the words in a context. The context means the word surrounding this given words. And CBOS means continuous bed of words. So it's a structure to the opposite of skip grant. So in CBOS training process, it will use the context words to recover the words in the middle. So let's wait for the word training to finish. Since we set a very small iteration number, this function should be finished in a short time. Okay, it finished in 105 seconds. The next, let's train the knowledge graph embedding. We use TransE to train the knowledge graph embeddings. The TransE is a very simple way to embed knowledge entities into a distributed representation vector. So this is his training objectives. So given a ground truth, heads, tails, and his relations, and it uses hinge lost to given any corrupted triples. The training process is to make the correct ones has a higher score than the corrupted ones with a certain margin. We use an open source implementation of TransE called FastTransX for generating knowledge graph embeddings, and the scripts, the command lines are all included in this bash scripts. So we need to simply run these scripts, and it will first clone the fast as repos and then trying to embedding. Since I already execute this folder in advance, so it is displayed that I cannot clone it one more again. But anyways, it can continues executes the following steps to train the transit model for the knowledge graphs. And for DKNs, it takes not only the entity embedding, but also the entity's context, which is his one hop's neighborhood, as the context embedding for this knowledge entity. So we need to further generate. It's a simple process to gather and aggregate each entity's surrounding entities embedding. Okay, it is finished. After you finish step 1 and step 2, now we are ready to train a DKN model. DKN model is originally designed for news recommendations, but it can be easily adapted to academic recommendations. This figure illustrates the motivations for DKN. Suppose we have two articles from their text content. We found that there are no overlapping words between these two articles. But with the help of knowledge graphs, we can observe that those knowledge entities are close related to each other with the help of knowledge graphs. So we can guess that if a user has clicked on the first article, then it will be very likely to be interested in the second article. DKN takes several files as inputs, including the training, validation, test files, and the user history file, document embedding files, and the word embeddings and anti-embedding files. After we execute the step 1 and step 2, so we already have all of these files. So let's first import some dependencies and set a tag for which to indicate which type of data set to run. Small means that we use the 10% of the entire data set for a quick demo, and also small data sets is usually used for quickly hyperparameter tuning. And then we set up some parameters for the file. If you fail to execute any steps in the previous two Jupyter notebooks, don't worry. Remember that when you download the data files, there is a folder named My Cache folder. You can find all the related files under this My Cache folder. So all you need to do, if you in the previous two steps, if you fail to generate any one of these files, you can simply copy and paste it to from the My Cache folder to your experiment folder, which should be data folders, my DKN training folder. So now I will suppose all the files are normally generated. So let's continue. Next, we will set up some important hyperparameters. The first is the number of epochs. For a quick demo, I will just set to 1, so the model will only train for 1 epoch. And its click nouns if set to true, it means that we will use gradient clips normalization. If a parameter's gradient is larger than 0.5, it will be cut off to 0.5. To avoid gradient explosion, history size means the maximum length of user behaviors for user modeling. And use entity and use context means whether to use the entity embedding and entity's context embedding in DKN. So if these two parameters are set to false, then DKN will not take any knowledge information into the model computation. These two parameters are used for aberration study. Okay, let's run this cell. And next, let's create a data loader for DKN and create an instance for DKN model. Now we have just got initialized DKN model. So we quickly test the model's performance. Because the model have not been trained so far, so in expectations, the model performance will be close to a random guess. Okay, so here we go. The LC is about 0.9, which is an AUC of near 0.5 means a random guess. So indeed, initialized model is near to a random guess. Let's train our model. This figure illustrates the framework of DKN. We can see that there are two core components of DKN. The first is KCNN, which is for document embedding. KCNN takes a multi-channel as input. The multi-channel includes a channel of word embedding and a channel of entity embedding and channels of entity's context embedding. And on top of this input, it will use convolution networks to learn the feature maps, and then use a mask pooling layer to get the final representations of the document. For user modeling, it uses attention networks to merge the user's historical behaviors into one vector we call the user embedding. The attention network will also take input of the target candidate item. That is to say, when we want to predict the preference of a user over a candidate item, we will use the candidate item as a query to calculate the importance score of each for each of the user's historical behaviors. And then the user's embedding will be an weighted averages of users' behavior histories. After we get the user embeddings and the item embedding, we concatenate these two embeddings into one long vector and feeds it through two layers fully connected neural network to get the final logits of clicks probability. So this is the overview of the computational logic of DKN model. Okay, let's. This fake function means we train the DKN model on training file, and the valid file is used for evaluations the model's performance on every epoch. So every epoch after we train the models, then we will evaluate the model on a validation file, and then our validation file is used for checking whether the model has reached an optimal state. And after that, we will Okay, so we can see that after 21 epochs, the AOC has already increased to a very high value. So it's above 0.9, and compared to initialized random states, it is improved a lot. And then so let's do a quick test on test sets. Uh, uh, Usually in our normal training pipelines, we use the validation sets for parameter tuning to avoid overfitting problem. Okay, we will see that the scores on the test sets is slightly different from the on the validation set, but it is still good enough. There is one more API to get the embedding of document. So if you are interested in info the document embeddings, you can use this API. Once gets embedding, so you can uh, designate which file you want to insert the embedding, and then this is the output file. So uh, it will output the embedding files for the input for a given input file. We can also test well if we don't use the knowledge information, what's the performance, how the DKN will perform. Then we can, to verify this, we can simply set these two parameters to false, and then runs the notebook again. So we denote this DKN model without the knowledge information as DKN minus. Here I list a table of the performance of DKNs on runnings on the full dataset. So because it takes a much longer time, so I'll just report the final results directories for now. So we can see that the metrics in this decrease a little if we remove the knowledge information from DKN. So to uh, to execute to reproduce this table's performance, what you need to do, all you need to do is to replace the text with the full, so it will execute the DKNs on a large data set. Light GCN is another is a baseline model, which is an ID-based recommendation model. I will introduce it later. Compared with DKN, Light GCN, although it's not a very fair comparison because DKN is a content-based recommended system, it uses pretty rich feature like the word embeddings and the entity embedding. But for Light GCN, it is an ID-based collaborative filtering model. It didn't use any content it didn't take any content as input. So at least here is just for a quick comparisons for different types of recommended models. Next, let's apply DKN to our second task, which is an item-to-item recommendation task. The goal is that given a research paper, we found a list of related papers as recommendations. Different from the user-to-item recommendations. In these scenarios, we don't need the user sequence because it is a non-personalized recommendation. So we only need the KCNN module from the DKN model for each item. After it goes through the KCNN module, it will produce an embedding vector for this item, and the similarity between two items will be is measured as the cosine similarities of their corresponding document embeddings. We train the model with softmax loss. Each time we fill the model with groups of item candidates, and the training objectives is that we maximize the corresponding softmax losses of the positives item. Now, again, let's first load some dependencies, and we set up some variables for the resource files. So we can observe that most of the resource files are reused from the user to item recommendation task, except the two instance file, which is especially for item to item task, and they has the prefix of item to item. And similarly, let's create a set of hyperparameters, which is against the sense with the user to item task. And for the epochs, we still set a very small number for a quick demo. In the DKN mod, original DKN model don't support the item to item task, so we need to make a little big changes of the code to enable this item to item facility. Most of the function can be reused from DKN. So what we need to change is only to add two new files, one for data loaders and one for model. For the now let's create an instance for data loader. The data format has been changed a lot from the previous user to item task. This time, we transforms the original positive pairs and appends with some negative families and transforms like this format. Let's say we use negative numbers of 9, which means for each one positive pairs, we will randomly sample 9 pairs of negative instance. And the input format is much simpler. So each line is item ID, and they are organized within groups. Within each groups, the first line is source item ID. The second line is the item ID of the positives candidate, and followed by 9 lines of negative items. Now let's create an instance for the item-to-item DKN model. And again, let's evaluate this initialized initialized model before we train it. It will take a few seconds. So let me introduce what has been changed in the news DKN item-to-item file. Actually, most of the functions are reused from DKN model. So we inherit the DKN class. What we change is only 1, 2, 3, 4, 5, 6 functions. And because we don't need the user embedding, so we only use the document embedding. So we made a small changes on the document embedding to add one transformer layers on the original KCNN vector, because the original KCNN components is use an activation function of the root, which will produce sparse vector to get because in our item-to-item recommendation task, our task is relies on a high quality of the document embedding. So we add this one layer transformations functions to make the document embeddings be dense and continue. And then with the logic function is so must, and the optimization logic is optimization function is to maximize the corresponding logics of the positive item. Okay, let's see whether the evaluation process finished. Okay, so we can see that even before we train the model, the model's performance on the validation set is not is far better than a random guess. So this is because that our similarity between two documents is measured by the cosine similarity of the corresponding document embedding, even for a random initialized model. So if the two papers have much words or entities in overlaps, then their document embeddings will be very similar. So that's why an initialized model have a high AOC even before it is trained. Let's see if we train a model, the metrics can whether the metrics can even go higher. And again, while it's executing, we will quickly go through the rest of the this this experiments. Again, for aberration study, we can set these two parameters to false to see if what happens if we don't include the knowledge information for the DK model. So I will paste the result directly to here, so we can see that again the performance will be drops if we remove the knowledge entities from the DK model. Okay, now we have one epoch results. So we can see that after training one epoch, the metrics increase significantly. So it means that the models can, the DK model can be learned effectively. Again, after we train the models, we can call the round get embedding API to infer any any files to get the papers embedding. At the last, I offers notebooks to illustrate how users can run live GCM on the Academy dataset. Live GCM is an state-of-the-art ID-based collaborative filtering baseline. It uses GCM to learn the embeddings of users and items, with the goal that low orders and high order user item interactions can be especially exploited into the embedding generation process. I will not go through the detail of these models, and we offer the notebooks just for the purpose of readers to experience how the other type of baselines can be run on the academic dataset. So users can run these notebooks by yourselves, and at the end of the notebooks, you can check the performance of the large GCM model. And because it is the metrics are run on the Shen test dataset, so it is can be directly compared to the DK model.
Is there any question for this module? Well, since we don't have too much time left, maybe we want to proceed with the next module. And audience, if you have any questions regarding to the previous ones, you just type directly in the chat box here. Yeah. So Alexander, can you please go to the next one?
Yeah.
Thank you.
Hello, everyone. Welcome to the module 4 of the tutorial. So this module 4 is about operationalization of knowledge graph-based recommender system. So my colleague Miguel and I myself, my name is Zhang. We are going to present this part. So in this module, we will basically cover 3 topics. In the first part, we will give the audience a brief introduction about the industry-grade graph database, some tools for computing, and including the commercial tools as well as the open source software tools. Secondly, the topic will be covering the introduction about the real-time scoring and the ranking for the recommendation system for industry applications. The last topic of this part will be a visualization of the knowledge graph data on CORD-19 dataset. Okay. First of all, let me just quickly give an overview of how the current industry applications are like about using knowledge graph to accelerate their business, right? So in the last a few sessions, we know that we know something about the basics of the knowledge graph, and we know how to use the knowledge graph to accelerate the recommender systems. And nowadays in the industries, actually, there are a lot of very interesting applications if we can expand the ideas and the practices into the industry-grade applications, right? So, for example, here we can see that these are the 4 key areas of the knowledge graph-based applications. So for the first one, on the left-hand side, you can see that there is the retail domain, where the knowledge graph actually has been used very, very heavily. People know that in the companies of eBay, Alibaba, Amazon, and Meituan. So Meituan is one of the biggest food delivery companies in China. So they all use knowledge graph for a few very interesting business application scenarios. Like for example, they can use the knowledge graph to do the customer experience enhancement, right? Like the knowledge graph can try to better understand the customer, and they can try to target the customer with particular products or particular service. And they also can do the targeted market campaign, right? So similarly, the market campaign can be segmented by using the knowledge graph or any other auxiliary information. For example, the review comments and images or any other useful data that can be used to augment the performance of the knowledge graph as well, right? So after the retail industry, we can see that actually in the financial industry, knowledge graph also plays a very, very important role. So we have a lot of evidence showing that the knowledge graph can help the anti-money laundering kind of application, because the graph itself can naturally connect the users in a transaction network, so that people can easily track all of the nodes where the transactions happen between the nodes, and the relationship between the nodes can be analyzed by performing some graph-based analytics, so that any abnormal behavior or any potential money laundering kind of activities can be easily captured by performing such kind of analytics on the graph, right? And also fraud detection is another very important applications of using graph in the financial industry. Also know your client, which is has been a very, very typical activity used in the banking service. So nowadays you can see that a lot of such kind of things can benefit a lot from the knowledge graph. And companies like Bloomberg, Refinitiv, and Financial, also IBM, they are doing a lot of interesting stuff around the financial applications by using knowledge graph. In the public good sector, we know that a lot of open source data sets like DBpedia, Yago, Wikidata, they have publicized their data set for the community to develop the knowledge graph based applications on their own particular scenarios. Right, and also I think just now we also reviewed the Microsoft Academic Graph as well. So this is something super, super important in the academic community as well. Like people can go there to check their citation and also like use the data to build a recommender system, right? In the internet industry, and not to speak too much about that because people already know that in the internet industry, knowledge graph has been used very, very widely and heavily, right? Like Google, Facebook, LinkedIn, Pinterest, they benefit a lot from the knowledge graph in their search engine and also recommendation system. For example, one of the very, very interesting use case in Pinterest is that they built one of the largest graph applications in the world to just provide the recommendations to their users. And that is super, super scalable, and it can scale up to billions of users, and still can maintain the real-time performance of the recommender system when it's deployed into their production system, right? In addition to the recommendation, knowledge graph in the industry of internet can also help the customer segmentation, right? So it's more like a course grade kind of recommendation that is to find a particular segment of the users, and then the graph can just particularly give the targeted audience with some contents or messages or whatever information that should be provided particularly to the group of people. Yeah. So let's go to the topic of the operationalization, right? So firstly, I would like to review this slide to just highlight the importance of the operationalization. So this might be something unfamiliar to academic researchers, but in the industry developers, especially for the companies who are building the production-ready knowledge graph-based recommender system, they should be aware of this, right? So the important thing for the production-ready recommendation system is that actually, as you can see in the diagram here, we try to depict the resources required and the time as efforts required for building a production-ready recommender system. Okay, so as you can see that the most resource-consuming work is around the data, right? So so why? Because a lot of times people need to collect the data and put the data into the right shape before they can really do anything. So that's why in the large company, they need to have a very, very healthy and a very, very proper setup of the ETL system as well as the data platform in order to pre-process and prepare the data to develop the recommender system, right? And then after that is about the selection of the algorithms. So that will involve a lot of the things like, you know, the ad hoc understanding of the business problem and the fine-tuning of the algorithm and even some customization on the state-of-the-art algorithms in order to make sure that the algorithm itself performs well in the, let's say, offline evaluation, right? The last part will be the operationalization. So what is the operationalization? So operationalization refers to the practices that, you know, deploy the whole pipeline into some infrastructure so that it can run in a regular way and be maintained in a regular way, right? So for example, if let's say we have a recommender system, so eventually the model, the data pre-processing pipeline, everything will be mapped into the infrastructure layer. Like, you know, you may use some big data storage, you may use some big data computing, and you may need to also use some front-end serving service to expose your API or endpoint of your recommender system, right? So all of this will be covered by the operationalization. And the biggest challenge of this part is to select the best service, best platform in order to make sure that everything works well all together, right? So let's firstly have a look at the industry practices that are, you know, that are well known in the few big tech companies, right? So here we have listed some big names of the companies as well as some institutes. So they develop the well-known products. And we also summarize their application. Like for Google, Google has the Google Knowledge Graph, and that is for the commercial application. It's used for representation of the data, right? And people particularly use that for data search, and it's a kind of enterprise application, right? And also we know that Microsoft has Satori, and several years ago, Satori, they also have a very comprehensive tutorial about how to construct a knowledge graph. And the knowledge graph itself can be built for data search as well, although this is for internal use of Microsoft, right? And just now we also, we have already covered the Wikidata and DBpedia, right? So both of them are open source, the knowledge graph application. And for other companies like Lenovo, they have their hypergraph. This is enterprise platform for building graph applications. And Facebook, they have Graph Search, which is a semantic search engine that is for providing a better user experience for their consumers. LinkedIn has its LinkedIn Knowledge Graph, and that is for you know, provide a better connecting analysis for all of the users on the LinkedIn website. And Amazon, they have their product graph. That is the graph that connects all of the products in Amazon, right? So you can sort of imagine that this is something to, get a profile of the products in Amazon so that it can provide a better recommendations to the users on Amazon. And Pinterest has the pin sage. So just now we have briefly covered the application of pin sage. So this implementation of the recommender system by using the graph convolutionary network algorithm. This is just to provide the very, very super scalable recommendation system for all of the users on Pinterest, right? So Uber, Airbnb, they both have their own graph-based applications respectively. Uber, they have the Uber Eats knowledge graph to enhance the recommendation system for their Uber Eats service with the aid of the knowledge graph, right? And Airbnb, they have also applied the knowledge graph for some context-aware applications. So when we talk about operationalization, so actually for the graph, the first thing we need to consider very, very super carefully is the graph database. So this is something like the key differentiator we have from the conventionally tabular data representation of the data set itself, right? So why we need to consider the graph database? Okay, so graph database actually it helps the data representation in two ways. So we can easily understand there is the if let's say we have all of the data already represented by the nodes and the entities and the whole thing. If let's say we want to capture the relationship of the data, right? So imagine you have the tabular data, right? So if you grow the data entries, let's say for the product data or for the data we show as an example down here in the slide, right? So if let's say you have some more data entries, when we call the data entries, we refer to the new entities added in the whole database, right? So let's say you have some new data entries. So the linear growth of the data entries will result in the exponential growth of the relationships between the data. You probably know what I'm saying. So let's say if you have one more data that you may want to have the join operation, and then that will give you both the complexity of the data representation itself, as well as the computation itself as well. So that is the downside of using the tabular data representation, especially when you have so many different sources of data together and you want to build an industry application on top of that, right? And graph database just promises a higher flexibility compared to the tabular database, right? So let's say again, so take a look at the diagram here we show on the slide. So if we think about the Twitter, right? So Twitter as an example, we know that people are connected in Twitter, and there may be billions of people connected in Twitter. I don't have the exact number of that connection, but it's super big, and the users, they may have their relationships like follows, and they may just follow each other, and or maybe they just have a unidirectional follow from one to another, right? So this is a very simple example about how the relationships can be built among the data entries, right? So then let's review what the problem can become if, let's say, we use the tabular database, right? So if you take a look at the right-hand side, if we use the SQL kind of query language, that is usually applied to the, relational database, right? So let's say you want to get the person's attributes, like person ID, and you want to also get the other information like the department where the person is working in. So you have to do at least 2 joins, right? You need to join the person with the ID, and you need to join the person with the department, because both the ID and department will be another table, right? So the 3 tables, they need to join together, and then you can get all of the information you need, right? Well, this kind of thing can be simply resolved by using the graph database, because you can just match the person with his relationship with another entity. Let's say, again, I mean, the person here will be in the graph database is an entity, right? Well, another entity is called department. So you can easily match the 2 entities together by using their relationship, which is works at, right? And then you can specify the attribute of the entities in order to make sure that you can filter out the correct results you want to retrieve from the graph database. So over here, the attribute will be the department name, which is the IT department. And then you can return the person's name so that you can finish all of the query result. And that is super, super convenient, flexible, and also conducts less efforts compared to the relational database, where there's a lot of drawing operations. So if we talk about the graph database, actually we're talking about the database model, right? So the database model corresponds to the database query languages. So actually, there has been a lot of efforts and a lot of progress in this field, and I just reviewed some of the most representative query languages that are commonly used in both open source community as well as the industry applications, right? So the first one is the language of Cipher, and it's a kind of declarative graph query language. It's used very commonly. So it is basically based on the property graph model, right? So that is to organize the data into nodes and edges. So remember, we actually have different terminology used in the graph world, right? And sometimes we refer the entities to nodes and the relationships of the entities to the edges of nodes, right? So they are the same thing. And in the property graph model, in Cipher, they just organize the data into nodes and edges, and they can query the nodes and query the edges, which are the relationships, in order to get the information from the graph database. Okay, so Gremlin is another commonly used query language, right? So it's a part of the Apache Tinkerprop program, and it's a graph traversal language, and it supports both the imperative and declarative querying. So it's actually also has a lot of industry implementation as well. So later on we will cover that in the next slide about how this query language are. So what kind of problem, what kind of platform implements the query language, and where it is supported, right? So Gremlin is very, I think it's a very mature kind of query language, and is used in some of the very well-known industry applications. And for example, in Microsoft on the Azure platform, the Cosmos DB service has implemented Gremlin language as an API for supporting the graph query in the service. The third one is called Sparkle, right? SparkQL. So this is more conventional. So it supports the Sparkle protocol, and it's more like a RDF query language. And the query language itself is very semantic. So it's used by a lot of developers in the community, and it's still very, very popular in the industry application as well. Yeah. So in the next slide, so let's review some of the supported platforms for the 3 different query languages. We know that in the industries, we have different platforms that can like support the query languages for really the industry level development. For Cypher, it's supported by Neo4j, and Neo4j, I don't think I need to cover too much about it because it's super well known, and a lot of people in the community they are using this, and also Agents Graph and the Redis Graph, they support the Cypher query language. Gremlin has even bigger commercial support. So you can find Gremlin support in JNS Graph, Infinite Graph, and just now I also mentioned that Microsoft cloud platform Azure, and there's a distributed database service called the Cosmos DB, and Cosmos DB has the support for Gremlin language as well. DataStax Enterprise supports Gremlin. And also another popular service on AWS platform is the Neptune, right? So for Sparkle, it's supported on RDF4j, Jana, and OpenLink Virtuoso, right? So these are the platforms that support the query language. So then after the database, a lot of the graph applications are built on top of the let's say, the graph data that has been retrieved or like obtained from a graph database. So let's say if somebody wants to build an application of the let's say, recommendation system or any other type of graph-related analytics. So we also like provide such kind of list of the summary about the open source tools that can help like operationalize the analytics by using different tools, and especially some of the tools, they're actually adopted in the production system in either the companies or the customers of the companies, right? So for example, Snap, and it's a kind of standalone tool that is open sourced by the Stanford research group, and is implemented in C++ and Python, and it's a general purpose network analysis and the graph mining library. The benefit of this tool is that you know, first of all, it's implemented in C++, so it's it has a very good performance. And in addition to that, it also provides the bindings of Python, so that the Python users and the developers, they can just easily extend the library by any Python classes, right? The second one is, I think, is more well-known, and a lot of people, not only the researchers, but also the industry folks, they're using that. Is called DGL, right? Deep Graph Library. It's implemented in the PyTorch framework, and it's open source on GitHub as well. And it's a very like a mature library, and it's providing a lot of very useful utilities for building the graph analytics and applications, especially the deep learning related applications on graph, for supporting a few different application scenarios like a recommendation, like graph-based clustering, and anomaly detection, so on and so forth. So it's also like implemented in C++, and it has a Python interface as well, right? So the third one is from Alibaba. It's called Ola, right? So Ola is implemented in C++, and it has a Python interface. So the highlight of Ola is that it's a distributed graph deep learning framework. So it's used in Alibaba's advertisement application. So it supports super big scale applications in Alibaba. You know, like in Alibaba advertisement, there will be very big scale computation required. And this is something that can work for the large-scale system. It can work with deep learning tools like TensorFlow and XDeep learning, and to support users to train models on the complex heterogeneous graphs with billions of nodes and tens of billions of edges, right? So some other tools like GraphNets, Spectral, Emling graph, and Stellar graph. So these are more like open source tools that are implemented in Python, and they support different types of applications. But in general, they can be used for building graph-related applications, either for deep learning kind of applications or knowledge graph applications. Yeah. So now I will pass on to my colleague Miguel to talk about the real-time scoring and the ranking for the recommendation systems.
Thank you, Lev. What I'm going to talk about now is how we can do real-time scoring in recommendations. And we are going through 3 different use cases, okay? The first one is a real-time lookup on a pre-score recommendation. So this is a use that is quite common, probably the most common use case. Then we're going to talk about real-time scoring based on approximate similarity matching. This is the use case that is done in search. Typical use case in search, how many search engines like Google, Bing, or others are implemented. And then I'm going to talk briefly about another use case, which is taking advantage of special tricks, optimization tricks. And this is designed mostly for GPU algorithms. So with the growth of deep learning algorithms, there is a need of being able to operationalize these kind of algorithms, and that requires different infrastructure and some tricks to be able to do it. Here we see the real-time lookup. The starting point is the data set. We will have user items, interactions between user and items, and maybe user metadata and item metadata. And this can be stored in any storage, right? It can be on Azure storage in a blob. It can be in a SQL database, and in a graph database as well. Then this is the data is taken, is loaded into memory on a compute target. In this case, you can see Azure Databricks in a Spark environment, but a similar approach would be on a virtual machine with GPUs or with CPUs, or even in a distributed GPU cluster. In the compute target, what we are going to do is we're going to do the complete training, evaluation, and similar to what Jianxun showed in the previous part of the tutorial. We are going to finally, at the end, when we have the model trained, what we're going to do is for each user, we are going to score all the recommended items, okay? And these results is going to be stored on a database. In this case, we chose Cosmos, but again, it can be done on any kind of database. Then, in order to serve this, what we will need to create is an API to be able to access this data, right? One good way of doing this is using Kubernetes. With Azure Kubernetes Service, we can create a Kubernetes cluster, and we will be able to generate this endpoint that we can show in a client, right? So at the end, the shape or interface of the API will be the input is going to be a user ID, and the output is going to be the set of recommended items. It can be 10 recommended items, 53, whatever number we want, right? And basically we are just doing a lookup in the database. So this is a this approach is commonly done in many e-commerces, and this is kind of the basic process. This process is repeated every day, right? Because the user behavior changes. There are new items coming into a store. There are some items that are gone out of stock, right? So normally, typically, the training process is done overnight. Obviously, you need to be careful that this process doesn't take too many hours. So maybe from 2 to 6 or to 8 hours is something reasonable. And then you need to create a pipeline to be able to do all this programmatically. So this will be the typical example of a ML ops, ML operations pipeline, right? You are basically recording or all the interactions on your page every day, and then you update these interactions to the Azure storage, and then when the starts, let's say it starts at midnight, the system needs to take the data, train, do the prediction and store the prediction in Cosmos, and then update the Kubernetes cluster if needed to be able to serve the latest items again. Now, the other approach, which is also this is the traditional approach for search, is the approximate nearest neighbor matching, right? In this case, the steps are the one. In fact, in the previous tutorial, Jianxun showed one item-to-item similarity, right? So this use case will be how to operationalize the item-to-item similarity, like the Jianxun explained. So the first step will be to compute the embeddings, right? The output of this will be item ID and then embedding. The size of the embedding will be whatever size it is produced by the algorithm, and then we have a large list of these embeddings. Now, the next step is to create the similarity index. There are several different algorithms for creating this index. Typically, they are divided in two groups: the tree algorithms and hashing algorithms. There are several open source libraries that can be used for this. One is Annoy, another one is Face from Facebook. There are a good number of open source implementations. The one problem with KD trees is that it doesn't work when very well when we have a large space of embeddings. So it's better when we have a smaller space. It doesn't scale very well. Hashing scales a little bit better in that case. So we will create this index similarity, and the next step is to be able to upload this index to a database, for example, Cosmos or any other database. Then on top of that, we will create an AKS cluster or any kind of system to be able to generate an API, similarly to what we did in the other example. Just one another way of doing this is instead of using a combination of Cosmos and AKS, another nice combination will be instead of Cosmos to have Redis, which is a cache database. It is very, very good for just lookups, so it's quite fast. And then for the API, we could use a serverless application like Azure Functions to generate the API. So that's another option, and it's also quite interesting. In terms of which one to choose, the option with serverless, typically they are not as scalable as a Kubernetes cluster, right? So if your business is a massive e-commerce, you probably want to have a Kubernetes server. If you have something smaller, a serverless option is okay. Then in order to access this, given the query, in this case will be the item query, we compute the embedding, right? And then with the approximate similarity model, we find the embedding that are most similar to the query, and that's what we retrieve, right? Now the final methodology is use some optimization tricks. There is a very nice paper from Alibaba where they show how they do their operationalization system for recommendations, and the idea is to have you need a big cluster of GPUs, and they have to be put in a distributed fashion, and also it's very, very important how you connect internally this cluster, right? So some optimization tricks can be to batch in the requests to be able to compute, to do the inference with several requests, so you can take more advantage of the memory of the GPU. Also, you can do GPU memory optimizations. Again, the objective is similar. We want to optimize and maximize the memory consumption on the GPU. And then another option is to use concurrent kernel computation. So this allows the computations to be processed in multiple CUDA kernels at the same time. Another very important trick here is how you connect. What is the connection that you have between the CPU and the GPU? So the bus that you use is quite important, and then how you connect different GPU machines, right? You also want to have a very low latency connection to be able to do this operation fast. Okay, so once we've seen the operationalization options, we're going to change the subject a little bit, and we're going to show a demo on how a knowledge graph can be visualized. So this is something that we actually have in our repository, in recommenders repository. So I'm going to change my screen, and we're going here, right? Just to give you, so this is the demo, just to give you an idea of basically the functions that we have here. These are the record utilities that can be found in recommended repository, right? We just need to go to record utils. Then here we have well, different sections. Azure ML for optimization, common dataset, evaluation or data evaluation tools, recommender, which is different recommendation algorithms that we have, and hyperparameter tuning. So if we go to dataset, here we have many different utilities for the datasets. We have the COVID and some downloaders. The one where we have the knowledge graph is here, Wikidata, because we have an example notebook to be able to query and create a knowledge graph using the open source Wikidata. So here here we have all the functions that are used in the demo. Yeah. This is publicly available right now. Okay, here we are going to just first read the data that we've dumped in the blob, and this is a very large data set. The structure that it has is this structure, right? So original entity name and all the linked entities and the name of the linked entity. So here we see the example. And the original graph has 50,000 rows. Okay, obviously to be able to visualize 50,000 rows is very messy. In fact, we tried to visualize it. It's like a big black point. It actually looks like the COVID itself. So basically what we did is we just took just 500 rows, and that's what we're going to visualize, right? Here we just need to generate the graph. This is how. So inputting the data frame, you just give the entity origin entity and linked entity. So this basically create the graph, and here we are just taking the names to be able to plot this, and after that we just plot the graph, and here we can see well some of the entities. So yeah, so here for example we see Argyriou, and well, these are some vaccines in Monet, and well, all the relationships between all these entities, which is interesting to explore. Yeah. Yeah, that's all for this part. Thank you very much for listening.
Yeah, I think we're just in time. And any questions regarding the last module? All right, if not, I will paste the link of the web page of the tutorial again. So if, in case you are interested in the slides, or if you are interested in the codes, anything, you can go to the website and you can go to the link that will direct you to the slides and codes used for the tutorial. Yeah, sure. So all of the codes and the slides will be available after the tutorial. Yes, I think the videos are already publicly available on YouTube.
Hey, I would just really thank you everyone for joining us for the past 3 hours, especially for those both in the audience or the presenter who are in a very awkward time zone to attend this. Yeah, I really appreciate that. So even you don't have any question now, but feel free to reach out to us if you have further questions. Yeah, I think we can be reached by our email. And yeah, thank you again for
Yeah,
taking the
exactly.
time to join us. Thanks.
Thank you so much. Thank you, Iris. Thank you, Jianxun, Miguel, Alexandra. Thank you all of your help to play the video. And thank you everyone, all of the participants of the tutorial session. And again, I mean, if you have any questions, just feel free to reach out. And yeah, hope you enjoy the rest of the virtual conference of KDD. Thank you. Bye-bye.
Yeah, thank you, Le, and thanks, Alexandra.
Thank you,
Thank you.
Iris.
Thanks.
Thank you, bye-bye.